Awesome. So, thank you everyone for joining. And today I will be talking about REVE, which is a new foundation model for EEG. And the title specifically states adapting to any setup with large scale pre training on 25,000 subjects. So basically, the question that it's trying to answer is, can a single EEG encoder learn useful representations across different tasks, montages, electrode layouts, as well as sequence lengths? So this is a particularly important question for EEG because as a modality, it is very different from images or from language. So in images, the input is usually a regular grid of pixels. In language, tokens are discrete words or subword units. But EEG is recorded from electrodes that are placed on the scalp. And the number and location of those electrodes can change from one data set to another. So a model that is trained on one montage, um, montage just refers to the placement of the electrodes on the scalp. So this model that is trained on one montage may not naturally know what to do when a channel is missing or when a new electrode appears or when the recording protocol is different. So the main goal of REVE is to build an EEG foundation model whose tokens are not tied to one fixed set of electrode identities. Instead, the model uses physical electrode coordinates and temporal patch indices to define where each token comes from. So throughout this talk, I will focus on how this is done. So first, we will go through the different steps of the architecture, and then we'll take a look at the results to see if their claim actually holds up. So let's start by first answering the question why EEG foundation models are hard in the first place. So the first point is that EEG is not a fixed grid. This is the basic motivation for the whole paper. Across EEG datasets, we have different number of channels, different electrode locations, different references, different sampling rates, different recording devices, and different pre-processing conventions. So unlike images where a pixel at a coordinate, say 1020, means the same kind of spatial location across images, EEG channels are not automatically standardized across datasets. So this creates a problem for supervised EEG models. So a model may achieve good performance on a specific dataset, montage, or cohort, but that performance may not transfer to a different acquisition setup. So, for example, a model that is trained on a 19-channel montage may not work well on a 64-channel montage, right? And this is not only a data size issue, it is also an input representation issue. So the challenge is not simply that previous EEG foundation models did not have enough data. The deeper issue is that EEG data from different data sets is not represented in the same coordinate system. If the model uses fixed learned channel embeddings, then the input representation is tied to one channel layout. So REVE's key move is to represent each token by physical electrode coordinates and temporal patch positions, so that tokens from different montages can still be interpreted in a common spatiotemporal space. So that's the main idea. Now, you might be wondering, why are we aiming for a foundation model? The idea is that instead of training a new model from scratch for each EEG task, we want to pre-train on a large and diverse EEG corpus and then adapt with linear probing or fine-tuning. And this is similar in spirit to what has already been done in LLPs and visions. But of course, with EEG, we have a few extra challenges. So basically, the model has to know how to interpret these different spatial layouts as well. So as I mentioned, REV's core idea is to use physical 3D electrodes plus a temporal patch position to make transformer tokens portable across layouts. So again, I'm repeating myself that the key technical contribution here is just positional encodings. and we'll take a look at how this exactly happens. So now let's try and look at this problem a little bit more formally. So on the left-hand side over here, we have an EEG signal X. We can think of it as a matrix X, which has a size C cross T, where C is your number of electrodes and T is the number of time samples. So each row is a channel and each column is a time sample. Now the electrode coordinates, which are the 3D spatial coordinates, can be represented in the space C cross 3. So for each channel, you will have 3 coordinates. So X, Y, Z, and this would be a particular coordinate on the scalp, which is specifying the electrode location. So obviously, we have to first tokenize this data. So in this case, the tokens would be channel time patch tokens. So each token corresponds to one electrode and one temporal window. The transformer then needs two kinds of information. It needs the signal content of the patch, and then it also needs the position of the patch. So what we need is a token position that means the same thing across montages. So in standard transformers, for example, in text, you might use the word order, or in images, you might be looking at a pixel or a patch location. But in EEG, we cannot simply take the channel index because the channel set itself changes across data sets, right? In one data set, I can have 16, but in another, I can have 64. So if you use a fixed channel index system for the positions, that is definitely not going to work. So older EEG transformer models, they tended to use learned channel embeddings. So basically, you learn the channel embedding you can think of it like a lookup table, right? So for each known channel index, the model learns one vector. If C is the channel and J is the patch index, then you basically just want to learn a channel embedding and a temporal embedding, and you can combine that with your patch embedding to get like a unified representation. Okay, so I'll just repeat this one more time. If you have a particular patch which is represented by C cross J, C comma J, then basically when you're learning these, you're using learned channel embeddings, you're just learning like a channel embedding as well as a temporal embedding and combining those together to have some representation of what a position would mean in an EEG. So that's the basic idea with learned channel embeddings. But these are essentially, they do not provide a principal representation for unseen electrodes on new montages. So, for example, say you have learned for a specific set of channels, you have learned some embeddings. Now, suppose a new channel is introduced, then the model has no pre-trained vector for it. And if a vector is added, it is typically untrained and not spatially meaningful. So similarly, when channels are missing or the montage changes, the model receives a channel configuration that may be out of distribution relative to what it has been pre-trained on. So without a continuous spatial description, the model cannot naturally interpolate between electrode positions or generalize smoothly, say, from one montage to another, right? So REV solution, as I mentioned, is coordinate-based embeddings. So in this, the position basically becomes a function of the physical coordinates. This means that if a new electrode appears, the model can still compute a positional encoding from its coordinates. And we will go into more details about how this actually works in the next few slides. So I just want to pause to ask if there are any questions up till here, and if the motivation is clear for why we are trying to do this.
Yeah, it's clear.
Awesome.
I
So
have one question though.
yeah, sure.
So this REVE foundation model you said is using coordinate-based embeddings, right?
Yes.
And like I'm imagining there will be people with different sizes of heads, right? So the
Yes.
XYZ for one correspond between subjects, right? So
Yeah.
uh, is
So
one.
definitely there is a little bit of distribution shift for sure because everyone has different head sizes. So the cap size with which you're measuring your EEG is also going to change. But when we collect the CEG data, the person who is collecting the data there is a protocol in which you take a bunch of measurements. So first of all, we try and align the electrodes to the exact same position on every person's head.
Mm,
So these caps are very specifically designed in a way that that distance is maintained. But
okay.
of course, there is human error involved, right? There is a person who is placing that cap, who is taking those measurements and ensuring that the vertex electrode is placed exactly at the same point for every person's head, right? That is something we try our best to do when we are taking EEG data. But
Okay.
your point is very valid, and there is, of course, a shift. And to account for that, these people actually add a little bit of Gaussian noise to the electrode coordinates to
Mm,
essentially add some robustness. But
okay.
that is definitely a limitation of EEG in general.
Okay. Thank
Yeah,
you.
awesome. So I will move ahead. So this is just a really simplified flow diagram of REV to give you an overview of what's basically happening. So like I mentioned, the raw EEG is split into patches. Each patch is divided into temporal windows of length W with an overlap of O. So this basically produces a tensor of patches of shape C, P, and W, where C is your number of channels, excuse me. P is the number of temporal patches per channel, and W is the number of samples in each patch. So this is fairly simple. Second, we pass the raw patch through linear patch embeddings. So the short EEG window, which was of length W in our patch, that becomes a vector of dimension, say DE, which is what they have used in the paper. This is similar to VIT style patch embeddings in images, but here each patch is a 1D EEG segment from a single channel. So then the third step is where we add in our 4D positional encodings. So for every token, the position is not just the channel index or the time index, it is a 4D coordinate. And we will look at what that 4D coordinate is in just a moment. After that, REVE uses block masking. So instead of masking random isolated tokens, it masks contiguous spatiotemporal regions. And this basically forces the model to infer missing EEG patches from neighboring visible electrodes and neighboring time windows. And finally, REVE trains as a masked autoencoder. And that is basically the overall flow of the diagram. And now we can actually go in and look at each of these steps to see what is happening. So the first step is tokenization. So this is fairly simple. We start with our raw EEG matrix of size C cross T, which means we have C channels and T time samples. Each horizontal trace that you see over here is a particular channel, and the time axis runs from 0 to T, as you can see over here. These vertical shaded windows are basically how REVE segments each channel. Each window has a length of W, and consecutive windows may overlap by an amount O. So the step size or stride between two adjacent windows is simply W minus O. And if the overlap is larger, the stride will be smaller and we get more patches. If the overlap is 0, then the stride is simply W and the patches will be non-overlap. So this is a fairly simple sliding window approach. The middle panel here, we have the results after segmentation. So instead of one contiguous time series per channel, we now have a grid of patches. And like I mentioned, our shape is CPW. So C is your channels, P is your number of patches, and W is the length of each patch. Um, so essentially, you can compute the number of patches in this way. This is a very usual sliding window count for full patches. So the term T minus W just tells us the last possible start point for a complete window. And then dividing it by the stride just tells us the last valid window start index um, uh, that we can have. And that is basically the formula. And we add this one to convert that into a proper patch count. And at the end, we have our patch embedding. So the raw window of length W is multiplied by a linear embedding matrix of size DE cross W. So this is your embedding matrix. And if you recall, your patch is of size W cross 1. So you end up getting a vector of size DE cross 1. And this is just your embedded patch, which is essentially what forms the token for the subsequent steps. Okay, so this was fairly straightforward. The next question that we need to answer is how to assign each token a position that works across montages, right? So the central idea is that each EEG token should be positioned by physical location and time. So each token corresponds to a pair, one electrode C, and one patch index J that you see over here. So REVE builds a 4D coordinate of that token. So it basically consists of the physical 3D coordinates, which are XC, YC, and ZC. These are scalp coordinates, which are usually derived from electrode metadata or inferred from standard electrode labels. The paper, as I mentioned right now, also adds small Gaussian noise to the coordinates during pre-training. The intuition here, like I mentioned, is that electrode placement and head geometry can vary across subjects and devices. So small coordinate perturbations encourage robustness. We also add a temporal coordinate that you see over here. So each patch has a discrete patch index J, and J runs from 1 to P, which is the number of patches. But what the authors argue is that the raw index may have a very different scale from the spatial coordinates. So what the paper does is that it scales the temporal index that you see over here, J, by a factor ST. So this makes the temporal coordinate numerically comparable to the spatial coordinate. And this is what we finally get for each particular electrode. Now we come to the third part, which is how have they encoded this? So there are two main ways that they have done this. The Fourier component over here is basically where they project this 4D coordinate into a multi-frequency sinusoidal feature space. So this is just like sinusoidal positional encodings. So this is basically a Fourier feature map of the coordinate. We are not decomposing the EEG waveform into any frequencies here. We are just encoding it simply in space and time. So here you can think of omega as a fixed frequency grid. So it is not a learned matrix. So it's fixed. So in the paper, they basically select n number of frequency per dimension, and they use a Cartesian product across all the 4 dimensions, so X, Y, Z, and the temporal component. This means that all combinations of the frequency across the 4 dimensions contribute to the encoding. So the way you can think of it is that suppose for each dimension, they select 4 frequencies. Then there are 4 choices for each frequency, right? So you have 4 choices for this X coordinate, 4 choices for the Y, 4 choices for Z, and 4 choices for T, right? So this essentially gives us 256 frequency combinations. And this matches the setting that you see on the slide over here. So the intuition here is that the low frequency components can describe coarse position, while the high frequency components can distinguish nearby positions. So that's the basic idea. You just have a bunch of frequencies, you take their combination, you multiply those with the vector over here, and you just embed them into this Fourier component. Okay, so what else do we have here? So the idea with this branch is basically that the model adapts the positional encoding to this Fourier space. But the problem with this Fourier space is that it is fixed, right? We are selecting a predefined number of frequencies. So although the encoding changes the input coordinates because it is coordinate dependent, the basis itself does not adapt to a specific data set or downstream task. So it is one of the issues with this type of encoding. It is also finite dimensional, which means we are only using a limited number of Fourier frequencies. And to basically address these two limitations, REV also adds a linear encoding. So this is basically what you see over here. It is a learnable representation of the same 4D coordinates. So this branch lets the model adapt the positional encoding to the EEG data and task. So with the Fourier component, everything is fixed. You have a predefined number of frequencies. You are embedding it using those frequencies. But they also add this learnable component to allow the model to be able to adapt these fixed encoded positional embeddings to the task and data that is being presented to the model. So basically, in this linear step, they are just passing this extended P coordinate through a linear layer followed by Galileo and Leah norm. So the final position encoding that they obtain is a combination of the Fourier encoding and the linear encoding, which is then used as a final positional encoding. So REVE can compute this P encoded for any electrode as long as it knows the coordinates. So this is why the model is not tied to a fixed channel embedding table. If a new electrode appears, the model does not need a new learned ID. It can just compute the positional encoding from the electrode's coordinates itself, as well as the temporal part. So is this okay? Any questions?
I have a question.
Yeah.
Okay. So XC, YC, and ZC, are these three also like how do you get these coordinates? How are
Yeah.
you measuring the coordinates from the cap?
Yeah.
How do you define that?
So generally, if you have a good data set and the people who have collected the data are kind, within the data set, in the metadata itself, for example, if you have EDF files for the EEG, in the metadata, you would have the electrode coordinates.
Okay.
They are provided per channel. So that is one thing if you're lucky enough to get a data set. So ANFI, which is a sleep staging data set, is amazing. It's an 83 channel data set and they have given the normalized coordinates for all the electrodes. So that's just one example. A lot of other data sets will do this for you. Another thing you can do is that when you get a data set, generally, if you look at the paper or the README associated, they will tell you what montage they have used, right? So they'll tell you it's a 10, 20, 64 channel montage.
Mhm.
So what you can do is you can just go and pick up the standardized 10, 20, 64 channel montage and pick up the electrode coordinates from there. That is slightly trickier because even in 64, 10, 20, it is possible that one or two of the electrodes might have been changed by the people who are collecting the data for certain reasons. So you're going to have to actually match the channel names to the standardized montage and see which of them overlap. So for REVE, they said that when they found a mismatch, like for example, for a particular channel, they didn't have the coordinates in the standardized montage, they simply dropped it.
Okay. But
Yeah.
and like these coordinate positions, they must be taken in reference to some channel, right?
So the coordinate positions itself would be fixed, right?
Yeah, but what is 000? Which one do you consider as 000? Probably should probably be
These
CZ, the
Yeah,
center
these
one.
things are generally standardized.
Hmm.
So I don't know exactly how they have standardized this, but for a 10, 20, 64 channel montage, your electrode coordinates should more or less align.
Yeah. Okay.
Yeah.
Okay.
My
And
one thing would be that sometimes it's possible that the units of the coordinates may be different, so just check that it's consistent. That's all. But
okay.
generally, it would be 3D Cartesian coordinates
Hmm.
specifically. Yeah.
Okay. And in this ST is learnable, right? Or how is ST computed?
It's a scaling factor. They have not said whether it's learnable or whether it's fixed. So we
Okay.
would have to go into the code to see that, but they have not explicitly mentioned it in the paper. They've just said they've scaled it so that everything is comparable. So I don't really know um,
Okay. Okay.
what's
Okay.
happening there. Yeah. And then it's just a simple sinusoidal encoding and plus a
Mhm.
linear component. That's learned. That's all. So that's pretty straightforward.
Mm.
Yes.
Okay.
I think Aditya had a question.
Just a simple question.
Yeah.
Like we have like two components, like the Fourier and the layer
Mhm.
norm genuine, the
Yes.
learn adjustment. Like, what is the significance of these two components here, and why
Yeah.
we are doing the layer norm after addition?
So the Fourier component basically gives you a fixed encoding depending on P, right? So you predetermine the number of frequencies that you want. I think in the paper they've taken three, if I'm not wrong. We can double check that. But basically, you pre-specify your number of frequencies, and using those number of frequencies for each coordinate, you can get a unique encoding. Okay, so that is the first thing that they have done because the idea within encoding is to get a unique vector corresponding to every particular coordinate, right? That the model can understand that, okay, this comes here, this comes here, this comes here. That's the idea. But because this Fourier component is fixed, right? It's only going to change based on the coordinates, right? It's not really dependent on the EEG data and the task. So in order to mitigate that, they added a learned encoding as well. So in this, the weight matrix that you see over here is going to be learned. So it's going to be dependent on the data at hand and the task at hand. So the idea here is that once you get this fixed encoding from the Fourier component, you may want to have some flexibility to adjust it based on what data you're getting.
Okay.
So that is the basic idea. And I think they took the layer norm at the end just to normalize everything.
Is the
Yeah.
concatenated. Okay.
Yes. I think that's just an implementation choice.
Yeah.
Yeah.
You.
Yeah. No problem. Any other questions? Awesome. Okay. So that's two steps down, two to go. Okay. Now coming to the next step. So this is basically our masking strategy. So it's pretty standard as well. Uh, so some tokens are going to be visible to the model, some tokens are going to be masked, and the goal is to make the model reconstruct the missing EEG patches using just the visible context. So this is standard for all transforms. So in the first panel over here, you have the full patch token grid. So everything's like before. The channels are columns, temporal patches are the channels are rows, temporal patches are columns, and each cell is one channel time location. So this makes it really easy to see that the masking can happen across two axes, spatially and temporally. So in EEG, we need to think about both of these and how we can leverage these two axes to make the masking a little bit more meaningful in this context. So an obvious simple option is just randomly mask it, right? That's what we always do. Um, but the paper argues that random masking can be too easy for EEG because EEG has a lot of local redundancy. So neighboring time patches often look similar and neighboring electrodes are often correlated in activity. So if we mask isolated tokens, the model may reconstruct them from almost identical nearby tokens without learning a very strong representation. So it's an easy trick that the model can get away with just because of how EEG data is. It's just a property of the data itself, right? So we need to do something a little more structured. So REVE therefore uses structured block masking. So this is shown in the second panel here. So instead of hiding isolated cells, it hides contiguous regions over space and time. So you have something called the spatial masking radius, which is RS, which defines how far around the selected electrode do you want to mask, right? And then you have a temporal radius, RT, which defines how far around a selected patch index should the mask extend in time. So using these two radiuses, you're basically able to define a contiguous region to mask out. And the paper also defines a masking ratio, which is MR, and we'll look at this a little later, which just controls the overall proportion of these tokens that are hidden during pre-training. So basically, after the EEG is divided into patches, MR determines how many of those patch tokens are masked and must be reconstructed by the model. So this masking ratio is determined empirically in the paper, and it's determined through ablations. The third panel basically shows you channel dropout. So what this means is that some selected masked regions, in those regions, the entire time series for a channel neighborhood can be dropped. So this is basically controlled by the dropout ratio right here that you see. So this basically controls the fraction of masked tokens that trigger this channel level dropout. And the dropout radius, RD, basically controls the spatial neighborhood that is going to be affected from this dropout. Okay. So the main intuition with this type of masking is that you want to make the reconstruction task deliberately difficult. So if nearby redundant patches are also hidden, then the encoder has to build a more global and meaningful representation. So it has to use more physically meaningful context from other electrodes and other time windows rather than just copying from almost identical neighbors. Okay. So that's the masking strategy. Now, once we have masked our different patches, we need a reconstruction pathway, right? So this is the last main step. Here we have our pre-training objective. So we can divide this into three main steps. First, we have our visible and masked patch tokens. So this is a masked autoencoder style reconstruction pathway. But they've also added a secondary global objective, and we'll look at that in a moment. So here we have our grid again, but as you can see, certain patches are visible while the other ones have been masked out by our masking strategy. Now coming to the second panel here, this is a MAE style reconstruction pathway. So the visible patch embeddings that you see over here, they receive positional encodings and go into the transformer encoder, and the encoder outputs our latent visible features. Okay, so this is pretty straightforward. For our masked tokens, REVE uses a learnable mask token. So essentially for the patches that we have masked out, it basically replaces those masked patches with a learnable mask token. So this is nothing but a placeholder that wants to represent the missing patches. So these mask tokens give the model a more controlled way to represent missing information while still forcing it to reconstruct that information from context. See, if you remove them completely, then the model's not going to know what to reconstruct, right? If you just turn them to zero, that is also not going to work because the model can interpret that as a flat channel or a distorted signal. So you basically want something that hides the information, but in a way that the model knows what is hidden and where it has been hidden so that it can grab the necessary context that it needs for the reconstruction. So this is the solution that the authors of REVE have landed on. So basically just replace all these mask patches with learnable mask tokens. And in this lower pathway, the latent visible features that are coming from here and the learnable mask tokens are brought together before the decoder. And the idea here is the decoder receives both the encoded visible tokens and the placeholders for the mask tokens with the positional embeddings re-added so the decoder knows where each token belongs. So that's the basic idea here. And then, of course, we have the decoder that reconstructs the masked EEG patches. The primary reconstruction loss that they have used is a simple N1 loss over the masked patch set. This equation is pretty standard. Here, PMI would be your original patch, and P hat MI that you see over here is the reconstructed patch. And the L1 norm just sums the absolute reconstruction error. Now, the question is that why L1? So the paper chooses L1 rather than L2 because EEG is inherently noisy and it can contain artifacts or outliers. So what they argue is that L2 would basically amplify the influence of noise while L1 offers greater robustness by reducing the impact of outliers. So that is why the primary loss is an L1 loss. Now, in addition to this main reconstruction loss, they also introduce a secondary reconstruction task. So this aims to reconstruct the mask patches from a compact global representation. So that's the main idea. So this is an extra objective beyond the usual MAE reconstruction. So how does REVE do this? What it does is that it takes the encoder outputs from multiple layers and it concatenates them, and it uses a learned query to basically perform attention pooling over these outputs from the different layers. And this basically produces a global summary token. So this global summary token has then been repeated, combined with positional embeddings over here, and then passed through a two-layer feed-forward network to reconstruct the mask patches. Okay, so that is basically what they have done here. And the idea is that this creates an information bottleneck. So the model must compress useful information about the entire EEG segment into one compact representation. So the total loss then that they have trained over is basically this primary L1 loss plus the loss from this secondary reconstruction objective. So the reason that this particularly matters is for representation quality. So a standard MAE can sometimes put reconstruction specific information mainly in the final layer. So the secondary loss encourages useful information to be distributed across the encoder and captured in a compact global representation. So this is particularly important for frozen feature or linear probing settings where we want the encoder representation to already be useful without requiring any heavy fine-tuning. So that's the basic idea of this primary and secondary training objectives. Okay, so any questions up till here?
So there are two reconstructions happening.
Yes,
One is
and two
from,
losses.
okay.
Yep.
So Okay, okay.
The main one is your L1 that is coming from the standard MAE style reconstruction pathway. But they've also added the secondary objective more in the context of EEG because they want that information to be distributed across the layers rather than just in the final one. So it helps with the downstream generalization. That's the idea.
Okay.
Awesome. And then, of course, after pre-training, the decoder is discarded and only the encoder is kept for the downstream tasks. And all the patch tokens are processed with the standard positional encodings.
Have they
Okay,
also have they
yeah.
also talked about like which of these two losses, like how they behaved over training, the primary and secondary loss?
I didn't see that, but they have ablated over this. So they did find that the secondary loss does improve performance.
Okay.
Yeah, but I did not see specific discussions on like how the loss itself behaves,
Mm-hmm.
but they
Yeah.
have ablated over it. So there might be something on it, maybe somewhere. The appendix was too long.
Mhm. Okay.
Yeah. Okay. So this is just the summary of the whole architecture, which is basically the figure from the paper. So it's fairly intuitive since we've already looked at all of these individual steps. So you have your 4D spatial encodings where you've taken the physical coordinates, added noise, two different types of encodings, Fourier, MLP, layer norm, that's your positional encoding, okay? Next is your patch embeddings, which is just the patches being passed through a linear layer. And the third is the block masking. So certain of the patches get masked out while others are visible. Um, these are basically passed to the encoder along with your positional embeddings. While for the mask tokens, you replace them with a learnable mask token. And that is basically then combined with the embeddings that you get from the encoder. You will re-add your positional encodings here and then pass it to the decoder, which reconstructs your patches. And that's the primary reconstruction pathway that the model uses. The secondary reconstruction pathway is over here, where you take the outputs from the individual layers. You do attention pooling using a learnable query, get a summary token, combine it with the positional encodings, repeat it, reconstruct. This is your secondary loss. So that's basically the whole summary of the model in one picture. Awesome. Any questions up till here? Okay, so I think we can move on to the next. Awesome. Okay, so what do we have next? So here I basically added this slide to show you that pre-training corpus. So the raw corpus that they have trained on is immensely large. It's 19 terabytes of raw EEG data across 92 sources, more than 150,000 sessions across more like 24,000 subjects with over 61,000 hours of recording. So it's a lot of data. And it is across clinical BCI and cognitive EEG recordings. One key thing that I want to mention here is that the electrode metadata is important because, like I mentioned, REVE relies on coordinates, right? So when that 3D coordinates are there, we can use them directly. Otherwise, like I mentioned, they infer the positions from the standard electrode labels, and channels without identifiable names or positions are essentially removed. So that's how they've sorted that. So REVE is more or less flexible, but of course you need to have those appropriate coordinate locations for this to work. After pre-processing, basically, what they've done is they've resampled all the data to 200 hertz, bandpass filtered between 0.5 to 99 hertz, which is like a very broad frequency range to consider, normalized with z-score statistics, and basically clip the signal if it goes above 15 standard deviations. So that's again pretty straightforward for an EEG pre-processing pipeline. Now, one important caveat here is that any setup does not mean that the model accepts any raw sampling rate directly. In the pre-training pipeline, remaining signals are all resampled to 200 hertz. So REVE is montage and layout flexible, and it can support different sequence lengths because of the way it is set up. But it is not the same as truly sampling rate invariant. Okay, so that's our pre-training setup. Next, we have the downstream evaluation data sets. So these are basically all the data sets that they have downstream evaluated their model on after pre-training. So as you can see over here in the table, the tasks are really diverse. So you have motor imagery, event classification, abnormal EEG detection, sleep staging, emotion recognition, mental stress, even imagined speech, which is really cool. So the table also shows why this is like really useful evaluation for REVE, because the channel counts are varying from 4 in HMC to like 64 channels for PhysioNet MI. The durations are varying from 3 seconds to 30 seconds. The class counts are varying from binary classification to 9 classes. So it's like a whole bunch of diversity in the data sets that they have tested their model on, which is really amazing. Now, for these downstream classifications tasks, for the evaluation, they have used a two-step strategy. So first, they train a linear probe on top while keeping the pre-trained encoder frozen. So the idea here is to align the classifier with the pre-trained feature space, okay? Next, they unfreeze the encoder and then fine-tune the entire network for task-specific adaptation. So the idea is that this will preserve the robustness of the pre-trained model. So importantly, this two-step strategy is implemented as a single continuous training run, where the backbone is initially frozen, so you only train the head, and then later unfrozen. So this approach is well suited for EEG data, where the distributions can shift significantly across data sets. So the primary metric that they've evaluated on is balanced accuracy. And this is appropriate because many EEG datasets can be class imbalanced. And balanced accuracy just averages recall across the classes rather than being dominated by a majority class. So it gives us a slightly better picture of what's actually happening. Awesome. So now we can move on to our main results that we have over here. So REVE base that you see at the very end in both of these, this basically leads on average across the reported EEG classification tasks. So this is the average performance of the models across all these different data sets. So if you see on average, the balanced accuracy is around 71% compared to 68 for Zebra mod, which is the strongest baseline in this table. So the average gain is about 2.5 percentage points, which is reasonable. This average gain is also meaningful because the comparison includes you have EEG foundation model baselines like Biot, Lebram, Zebra-Mod, and you also have non-foundation model baselines like EEG-NET, you have EEG Conformer, and a bunch of different EEG-based models. But An important point here is that REVE is better on average, but it is not uniformly better on every single data set. It is better on majority of them. So, for example, REVE shows a really large gain on the BCI 4-2A data set, which is right here. And it also performs well on MAT right here. But on ISRUC, it is a little bit lower, barely by a margin, as compared to CBRA-MOD. So it's doing a decent job across a whole bunch of tasks and improving significantly in some of them. Okay, so that was their main results. We can also take a look at the representation quality. So this table is essentially trying to answer two questions. First, does the pre-training actually help? And second, are the learned features useful even when we have frozen the encoder? So the top row here shows models with pre-training. So here REVE base gives the best balance accuracy among the listed pre-trained models. So with full downstream adaptation, which is this first section over here, REVE is competitive and it performs the best on the PhysioNet MI dataset with 4 classes, which is what they have tested this on over here. The middle row basically compares the models without pre-training. So this is important because REVE without pre-training drops quite a lot. So the architecture alone is not enough. The masked autoencoder pre-training is a major part of why REVE works. And the bottom row shows the frozen setting for the PhysioNet dataset. So here the encoder is not updated, only the classifier is trained on top. Of course, this is a stricter test of the representation quality. So REVE base remains stronger than the other frozen foundation models, which suggests that its pre-trained encoder already contains some useful EEG features. So it is, of course, not as good as the full fine tuning, but it is still better than the baselines that it has been compared with. So the main takeaway here is that REVE benefits strongly from pre-training, and its advantage is especially clear when we freeze the encoder and test the quality of the learned representations. Now, they've also done more detailed tests on linear probing. So the previous table that we saw was just on the PhysioNet MI. So in this table, they look at linear probing across a much wider set of downstream EEG datasets. So here, the pre-trained encoder is kept frozen and only a simple classifier head is trained on top. So this table is basically testing how useful the pre-trained embeddings are across different tasks out the box. So the main result here is that REV performs much better than CBRA-MOD on average in the linear probing setting. And REVE large gives the strongest average performance, which supports the idea that scaling the model produces richer and more transferable EEG embeddings. They've also tested with pooling and without pooling. So pooling helps in some datasets, but not in all. So again, the main takeaway here is that REV's frozen features, especially from the larger model, transfer better across different EEG tasks. And this is particularly important for practical EEG applications, like when you're thinking about real world applicability, right? Because in many settings, especially in BCI calibration or clinical deployment, we may not have enough labeled data to fine tune a large model, right? So a representation that works well with a frozen encoder and a simple head is valuable. It is really valuable because it reduces the amount of task-specific data and computation required, right? And this is like a challenge that I faced a lot because with sleep deprivation data sets, they are very small. So like one of the data sets I'm using just has 28 participants, right? So it's not enough to be able to fine tune these really large models. So if we have something out the box that has good learned representations that can do a decent job, then that is something that is very meaningful for EEG especially. So we can also take a look at some of the aberrations. So I've just summarized them here in a table. The first takeaway over here is that the secondary loss matters. Removing it reduces both linear probing and fine-tuning performance. The average linear probing result, when we have the secondary loss, it improves from 52 to 55. And for fine tuning, it improves from 61 to 65. So the global token objective is genuinely contributing to the representation quality. The second takeaway is that block masking matters and that the mask ratio matters. So in the ablation, what they found was that the masking ratio of 55% gives better average full fine tuning performance. So the intuition is that 25% masking may be like too easy because too much redundant information is there, and 75% may remove too much of the information. So 75 is doing a decent job for them. The third takeaway is about the positional encoding and the variants. So basically, they've looked at the 4D positional encoding that they used, a learnable positional encoding, as well as an MLP-based positional encoding. So this MLP-based MLP 4D is basically where the model still uses the 4D coordinates that we talked about, but instead of encoding it with a Fourier-based positional encoding, it just passes the coordinates through a simple MLP to produce the positional embedding. And this is basically testing whether using the Fourier structure itself matters. And what they found was this MLP 4D actually performs worse than the full 4D PE with the Fourier encoding. So this basically suggests that the fixed Fourier features are actually providing a useful inductive bias beyond simply just giving the model the coordinates. For the learnable positional encodings, what they found was that they are competitive in domain. But of course, we've already discussed the disadvantages. They do not naturally extend to unseen layouts or longer windows. And that's just a limitation of learned embeddings. So basically what they found was this 4D PE does the best job. The fourth thing is that they tested a whole bunch of layer norms and activation settings, and what they found was that the gated GALU plus RMS norm does the best job. In their appendix, they also had these additional results where they have actually tested the model for sparse setups, which was a little interesting. So what they found was that REVE degrades gracefully when channels are removed for motor imagery. So this is for the motor imagery left and right. So it is not 4-class, it is 2-class. Classification, and what they found was that the performance basically drops from 82 with 64 channels right here to 66 with 1 channel, which is honestly really amazing. But it could be that motor imagery is not very sensitive to the number of channels that you have. So if there are like a bunch of key channels that are doing all the heavy lifting, then it is possible. I don't know. But for imagine speech, which can be a little bit more sensitive to channel sparsity, you see that the performance drops below chance. So, I mean, the takeaway from this, I guess, would be that montage flexibility is very, very dependent on the task. And if the task requires broad spatial information, then losing channel information can be harmful, right? For example, for sleep staging, right? If you have a 83 channel data set and you start with, say, 83 channels, and you bring it down to like 4, it will still do a decent job because we know we can do sleep staging with just 1 or 2 EEG channels, right? So it's very, very task dependent on how this performs, how you interpret this. Okay, and I think the last thing we can look at is the limitations. So REVE is definitely a major step forward towards montage flexible EEG foundation models. But like I mentioned, the phrase any setup comes with a few caveats. So the first limitation, like I mentioned before, is sampling rate handling. So the pre-training and evaluation pipelines, they all resample the signal to 200 hertz, and this means that REV is not truly sampling rate invariant. So that was the first limitation. The second limitation is the input constraint. So the paper notes that signals need to be at least 1 second and you need multiples of 1 seconds. So even though the positional encoding supports variable sequence lengths conceptually, the implementation still has certain practical constraints. The third limitation is data imbalance. So the corpus is, of course, extremely large, but public EEG data sets are still biased towards certain regions, clinical data sets, acquisition practices, and populations. So in the limitation section, the authors have mentioned more selective and equitable curation is an important future direction for these types of foundation models, because at the end, that's the idea, right? They should be able to generalize to any participant, right? And given the sheer amount of inter-subject variability in EEG, it's very, very important to have a good representation in your pre-training corpus. There's also the physiological interpretability. So coordinate-based is definitely a meaningful direction. But we still need some work to understand like what these representations might mean, like neurophysiologically, right? Like they have not done that side of the analysis. Like, is there some interpretable or neurophysiological insight that we can actually grasp by using this coordinate-based system? So that would be an interesting question to answer. There's also a privacy concern that they mentioned, which is basically that the decoder is trained to reconstruct EEG, raises the question about how much signal information is recoverable from the latent representations. The decoder is discarded after pre-training, but reconstruction-based self-supervision still has some privacy concerns, because for a lot of the data sets that when you sign like an agreement to access the data set, they generally have a clause in there saying that you will not attempt to, reconstruct some of the information that has been anonymized. So EEG definitely has some subject specific um, signatures in it. So that's just like a different discussion to think about, honestly. So basically, the summary of this whole thing is that it's definitely a really great step forward towards like flexible montage models. Another thing is that they've not explicitly talked about the montage. Like they've just said that, hey, in the pre-training, there's a bunch of montages. So it may work, I guess. They did mention that they also tested it on a bipolar montage, which was not present during pre-training, and it tended to work. So maybe it works, but there hasn't been like a really dedicated analysis of like, hey, we pre-trained on a totally different montage and we tested it downstream on a totally different montage. But that would be really cool to see if it works or not. Okay. So there's still some work to be done here, but it's definitely a really cool step forward. And I will basically stop here. And if anyone has any questions, I would be very happy to answer.
Anybody has a question? I don't think so. It was a really good explanation.
Yeah, it was honestly like pretty. There are some cool EEG specific things that they have done, but more or less it was like a masked autoencoder strategy for pre-training. A lot of the things were pretty standard. They've introduced some little quirks that are EEG specific that seem to be working very meaningfully in the context of EEG. So I guess there's something to be learned here.
Yeah. Thank you for such a great presentation there.
No.
Thank you so
All
much.
good.
Wonderful presentation.
No, all good.